It's kind of weird. We have these incredibly powerful AIs that can create breathtaking art, write poetry, even generate complex code, but they seem to have the memory of a goldfish. Seriously, you can teach one to be a world champion at a game, but the moment you try to teach it something new, poof, it's like it forgets everything it ever knew. Today, we're going to solve this mystery. So this is the big question, right? Why this digital amnesia? This isn't just some random bug in the code. No, this is a massive fundamental challenge called catastrophic forgetting. And honestly, it's one of the biggest roadblocks preventing us from building AIs that can truly learn and grow over time, just like we do. So what is going on under the hood?
Okay, so here's the main difference. The way we train most AIs today is basically like cramming for a final exam. You give it a giant, fixed textbook of data, it studies like crazy, takes the test, and that's it. It's frozen in time. Continual learning, on the other hand, well, that's what we do every single day. We learn, we adapt, we pick up new skills without just tossing out the old ones. It's the real holy grail for artificial intelligence.
All right, so let's get into the weeds a little bit on this problem of catastrophic forgetting, because this is really where the dream of building a true general artificial intelligence hits a massive wall. So picture this. You've trained an AI to be an absolute expert at recognizing cats. It's flawless. Now you decide to teach it how to recognize dogs. What happens is, in the process of learning dog, the very neural connections in its digital brain that stored the cat knowledge get rewired and completely overwritten. The result? You now have a world-class dog expert that has no idea what a cat is anymore. It's a one-in, one-out system, which is just not how we work at all. And this quote right here just nails it. This isn't some minor engineering hiccup we can just patch over. It's a deep, foundational chasm between how our current machines learn in this static, isolated way and how living things learn, dynamically, continuously, for a lifetime. So how in the world do we even start to fix this? Well, believe it or not, the first clues don't come from computer science. They come from the fundamental laws of physics. Yeah, that's right. It turns out the very reason learning is possible is baked into the fabric of reality itself. Our first big clue is something called locality. All that means is you don't need to understand everything happening in the entire universe just to figure out why an apple falls from a tree. Cause and effect are local. And this is huge because it means we can break the world down into chewable, bite-sized pieces and learn about it step by step. Without that, learning would be impossible. And our second clue? Symmetry. Think about it. The laws of physics are the same here as they are on the moon or in a distant galaxy. Gravity is always gravity. This means knowledge is reusable. What you learn about how a ball moves in one place can be transferred or generalized to another. It's what allows us to build knowledge on top of other knowledge, to have it accumulate over time. Now, get ready for this, because this one is absolutely mind-bending. It comes from thermodynamics. Landauer's principle tells us that erasing information, forgetting something, isn't free. It has a real physical energy cost. So every time a system erases a bit of memory, it has to dissipate a tiny amount of heat. This strongly suggests that any truly efficient learning system, like our brain, has to be incredibly smart about what it chooses to forget. Okay, so we've gone from the cosmos down to physics. Now let's zoom in on biology. Because the human brain is the ultimate existence proof. It's living proof that continual learning isn't just possible. It can be done with staggering efficiency. So, what's the brain's secret weapon? Well, it's not one single system. It actually uses what are called complementary learning systems. Basically, it has different specialized parts that work together in a beautiful balancing act. One part is great at learning new things super fast, and another is great at protecting and integrating that knowledge for the long haul. And here's how that two-step dance works. First, you have the hippocampus. Think of it like a super fast memory buffer. It immediately grabs all the details of a new experience. But that's short term. For the long haul, you have the cortex. This is a much slower, more deliberate system that carefully weaves that new information into your existing web of knowledge. And get this, a huge part of that integration process happens while you're sleeping. While we're asleep or even just resting, our brains are hard at work. They literally replay recent experiences, almost like watching a movie, to strengthen those important neural connections. It's like practice, but on autopilot. And biologists call this, fittingly, memory replay. And this is where it all clicks together.
AI engineers looked at this biological process and had a light bulb moment. They built a technique directly inspired by the brain called experience replay. The AI keeps a small memory bank of past experiences, and as it learns new things, it mixes in and replays some of those old memories. It's a beautifully simple, bio-inspired solution to that catastrophic forgetting problem. So, armed with these incredible clues from physics and this amazing blueprint from biology, how do we actually go about building AIs that can learn for a lifetime? Let's look at the concrete engineering strategies that have come out of all this.
As you might guess, there's no single magic bullet. Instead, researchers have developed a whole toolkit of different strategies. Each one has its own pros and cons, but they're all aiming at the same thing: curing AI amnesia. And this table gives us a fantastic bird's eye view. You've got approaches like regularization, which is kind of a gentle approach. It basically tells the AI, hey, try to learn this new thing, but please don't change the important old stuff too much. It's cheap and easy. Then you have replay-based methods, which we just talked about. Super effective. You also have what's called dynamic architecture. This is wild. The AI literally grows new brain cells, new neural components to handle new tasks so it doesn't have to overwrite anything. It's amazing for preventing forgetting, but as you can see, it's very expensive. And then check out the one near the bottom, prompt-based. This is a newer idea, where you use prompts to guide these giant pre-trained models. And look at the results: strong forgetting prevention, but with incredibly low memory and compute costs. It's a real game changer. So, we have made some absolutely incredible progress. But the journey to a truly lifelong learning machine is definitely not over. So what are the big unsolved problems that researchers are staring down right now? Well, there are a few big ones. First, there's a hardware problem. Just moving data from memory to the processor on our current chips uses way more energy than the actual math. It's a massive bottleneck. Second, our learning systems are often rigid. They learn at one fixed speed. But biological systems are way more flexible. They know when to learn fast and when to take it slow. And third is this fascinating, almost paradoxical problem. Some of the most advanced AIs can literally overthink. After a certain point, more computation actually makes them worse. They'll find the right answer and then keep thinking until they convince themselves of a wrong one. And that really brings us full circle. The solution to AI amnesia isn't just about finding a clever algorithm. It's about building systems that are aligned with the fundamental rules of our universe. The simple fact that reality has a structure, that it has these properties of locality and symmetry, is the only reason learning can happen at all. So maybe the ultimate goal isn't just to build a better AI, but to build one that truly grasps the beautiful, learnable reality that it's a part of.